Welcome to the Math 3 lesson summary video for the task Flipping Ferraris. The purpose of this task is to extend understanding of inverse functions to include quadratic and square root functions. In the last task, you looked at some examples of inverse functions within the linear function realm, but in this task we're extending that understanding to other types of functions, specifically quadratic and square root. So we're given in problem 2 this function rule for a Ferrari that gives us the stopping distance when we slam the brakes based on the speed of the car. So as you can see in my table, if I was driving at a speed of 25 miles per hour, it would take me 18.75 feet to stop because our speeds are in miles per hour and our distances here in this function are in feet. If I was driving 50 miles per hour, it would take me 75 feet to stop, 100 miles per hour, 300 feet to stop, 200 miles per hour, 1200 feet to stop, and 300 miles per hour we learn later in the task is actually not possible because they tell us at a later point that the maximum speed of the car is about 217 miles per hour. But we have this graph. We've restricted the domain to only be positive values because we can't have a negative speed. So in this context, it doesn't make sense to graph the negative side of the domain of this function, so I've only graphed the positive quadrant. And you can see those points on the table and how they create a quadratic function on the graph. So question A asks us to determine how many feet we would need if the car in front of us was traveling 55 miles per hour. So at 55 miles per hour, the stopping distance we would need between us and the car in front of us is 90.75 feet. And that is assuming they somehow instantly stopped. Question B asks us what distance should we keep between us and the car in front of us if we're driving at 100 miles per hour, and we can see that answered already at this row in the table. 100 miles per hour, we need 300 feet to stop. And that came from substituting 0.03 times 100 squared to get 300, and in the previous question we just did 0.03 times 55 squared, doing the squaring first based on order of operations. And that's all based off this function rule at the top. We're just substituting in for these questions. And then question C says if the average car is about 16 feet long, how many car lengths should you have between you and the car in front of you? Well, if we know it takes 300 feet to stop at 100 miles per hour and the average car is 16 feet, then dividing, we can determine we would need 18.75 car lengths between us and the car in front of us if we're driving at 100 miles per hour. Though I'm not sure where you could legally drive 100 miles per hour around here, it's probably best not to do that. Moving on to question 5, they change up the scenario a little bit. Instead of being given speeds and trying to figure out the distance that we would need to stop at those speeds, this time we're taking our function rule, same function rule, and we're being given a distance. So it says in this problem, what if the driver of the Ferrari 550 was cruising along and suddenly hit the brakes to stop because she saw a cat in the road? She skidded to a stop and fortunately missed the cat. When she got out of the car, she measured the skid marks left by the car so that she knew that her braking distance was 31 feet. So it says how fast was she going when she hit the brakes? In this case, we need to substitute that distance of 31 feet in for d in the function rule, or d of s, giving us this equation 31 equals 0.03 s squared. So instead of substituting into an equation and just doing a calculation, here we have to solve an equation. So first we'll divide both sides by 0.03, leaving us with 1033.3 repeating equals s squared. And then we'll square root both sides of the equation, giving us our answer of 32.15 miles per hour. That's how fast she was going when she hit the brakes to save the life of that dear sweet cat. Same type of question in question B. You would follow the same process, substituting 15 in for distance and then the same steps to solve. So pause the video and try this if you haven't already. So you've already tried to solve question B using the process you saw from question A. The answer you should get would be 22.4 miles per hour. Skipping ahead to question 7, it asks us to use that kind of thinking and go ahead and solve this equation for s so that we get a new function that tells us the speed the car was traveling for any braking distance, so an S of D function. So in order to do that, again, I'll first divide both sides by 0.03, leaving us with D over 0.03 equals S squared, and then we'll square root both sides of the equation, leaving us with S equals the square root of D divided by 0.03. And to write it in the form they've asked us, it would look like what you see in the lower left of your screen. Moving on to the next set of questions, questions 7, 8, and 9, it asks us to go ahead and plot a table for that. I've just taken my original table that we already saw back in problem 2, and I've switched the values because I know that all these values are the same. So 25, 18.75 is now 18.75, comma 25. And that reminds us that these functions are inverses. So one way I can see that these functions are inverses is because they have opposite operations in the reverse order. So in the d of s function, the blue function on the graph and the blue table and equation, we square s and then we multiply by 0.03. In s of d, we do the opposite operations in the reverse order. So the last thing that was done in d of s was multiply by 0.03. The first thing that's done in S of D is the opposite of that, to divide by 0.03. So we're doing the opposite operation, and the last thing is now the first thing. The square becomes inverted as a square root. So you can see we have opposite operations in the reverse order. Instead of squaring and multiplying by 0.03, I'm dividing by 0.03 and then square rooting. Similarly, as I've already mentioned, you can see from the table that the x and y values are flipped. So another example, 100, 300 in the blue function became 300, 100 in the green function. And finally, the graphs are a reflection of each other over the line y equals x. As you can see, I've drawn the line y equals x here to make that clear. So since all three of these things are satisfied, we know that that means these are inverse functions. D of s is the inverse of s of d. Finally, the task ends with a couple problems asking us to consider this idea of restricting the domain. So if I did not restrict the domain of this function, so we restricted it to only positive speeds based on the context, but if we ignored the context and considered theoretically this entire function, this entire quadratic function, it would look like that. And the inverse, in this case, would now look like that. So is that inverse, that green graph, a function? And we can see if we draw a vertical line, it crosses twice at several different places, therefore it's not a function. Since this inverse is not a function, that means the original function is not invertible. So you can see I've taken this vertical line and I've placed it up here in its corresponding point on the original graph. So there's something called the horizontal line test to see if a function is invertible. So to see if something's a function, we've used the vertical line test in the past. A vertical line can only cross through the function at one point. To determine if a function is invertible, we can use something called the horizontal line test, which says that any horizontal line that I draw through the function should only pass through it at most one point. And that would be for an invertible function. Since this horizontal line passes through twice, it's not invertible unless we restrict the domain. So to summarize, we know a function is a relation where every x goes to one y. But what makes a function invertible, as we considered in the last slide? Well, in order for a function to be invertible and to pass the horizontal line test I just discussed, it has to be a function where every x goes to one y and every y goes to one x. And that is called a one-to-one function. So only one-to-one functions are invertible. Visually, the way we can tell that something is a one-to-one function is the horizontal line test that I mentioned, which says any horizontal line only passes through the function at most once. So as you can see, when we restrict the domain, now it becomes an invertible function on the restricted domain because any horizontal line I draw is only passing through our original d of s function one time, and that's why we were allowed to create the s of d function as its inverse. Thank you for watching. Hope you have a great rest of your day, and if you need help with the Ready, Set, Go homework problems, please check out the Canvas site for your course and the Ready, Set, Go support videos located there.